correspond to minimal surfaces. So of different types. So for the first problem, so the Laplace eigenvalue on closed surface, that's minimal surfaces in spheres. So that's minimal surfaces in round spheres, Sm. So that goes back to the work of Nadirashvili, and then also El-Zufi and Elias. And then in the second case, that is boundary minimal surface symbols. So free boundary minimal surfaces in Euclidean balls. And so that goes back to the work by Fraser and Schemer. Okay, so what I mean here by correspond to, I mean it's induced by such metrics. So so corresponds to means meaning that for one maximizing metric is induced by minimal immersion from the surface to some sphere. And then the same thing for the second thing, and similarly for the second, and similarly. So what you can do now is, of course, you can try to solve these maximization problems to find examples of such minimum surfaces. So let me tell you a bit about the history of the story. So, so this maximization problem, at least in the closed case, is kind of a classical thing. So maximization problem, at least the first one is kind of classical. One is classical. And it starts with the famous first bound. So starting with Hirsch's work, which was in the 70s, which gives the case of the surface being the round sphere. Not the sphere, I mean, being the sphere, and then you allow all the metrics. And so then the story continues. So quite a while later, so Nadirashvili in 96, I think, right? He did the case of the two torus. And so let me emphasize that that work is like quite different from what has been done before. So Hirsch is kind of the classical thing. You prove an inequality, and then you just happen to know that the inequality is separated at some metrics, in that case, the round metrics. So Nadirashvili is very different. So he proves that there is a maximizing metric, and then for other reasons, you know what that maximizing metric has to be. And then you get the sharp bound on top, right? But the real thing there is to prove the existence of maximizing metric. So then there's also work on like a few other cases, but always takes quite a while until things move on. So then also Nadirashvili, and then there's some other names to mention. So there's El-Zufi, Giacomini, and Jassar in 06, and then you should also combine this with more recent work of Chanki, Kalpukin, and Medvedev. So that gives the case of the Klein bottle. So it's the Klein bottle. And then much more recently, so there is work by Nayatani and Shoda giving this case of the surface of genus 2, so genus 2 surface. And so in all these things, what is proved is that an explicit maximizing metric is identified. And so here, so actual, I mean, I'm not talking about what's actually happening there, but the thing that they prove and that's happening. So that was conjectured earlier, by, okay, so I don't have it in alphabetic order, I'm sorry, by Hoterovich, Nigam, Jacobson, Levitin, and Nadirashvili. Okay, when I introduced the problem, I only talked about the first eigenvalue. So you can also talk about the entire story for high eigenvalues. It's for some reasons quite different. I don't want to get into that. I just want to mention that there's a lot of particular recent work on that problem. So a lot of recent work for corresponding problem on higher eigenvalues. Okay, I'm just giving you a list of names, and then there are all sorts of collaborations between those people. So there's Nadirashvili, Penskoy, Poterovich, Kapukin, and also. Okay, so that's kind of the story for the closed case. Starts back in the 70s, but kind of keeps developing, always takes some time, and a lot of recent work. So for the Steklov problem, the story is a bit different. That was only kind of became fashionable in the last like maybe decade. So for Steklov, there is a lot of work by Fraser and Shane. So also on higher eigenvalues. And then the thing I maybe want to emphasize on okay, so the parentheses are suboptimal. So they have work on higher eigenvalues, and then work on the first eigenvalue is particularly in the case of like surface of genus 0, on surface of genus 0. Okay, so that's a bit of the history of the problem. So now let's see what we proved. So here's the first theorem, which is jointly with Anna from last year. And it just says, well, you can solve this maximization problem for the first eigenvalue on a closed surface. So let's sigma be a closed surface. Then there's a metric. Then there is a metric. So it might not quite be smooth. It's still not totally clear if the regularity is optimal, I think. So it's smooth away from at most finitely many conical singularities. Such that you maximize. So such that you have that lambda 1 sigma comma h, area of that metric is at most the quantity for G. For any smooth metric H. And then, so in particular, so I put this in here, so in particular, we find possibly branched minimal emergence from that surface, that given compact surface, into some sphere, Sn. So that induces the metric G. And so, to the best of my knowledge, these are new examples of minimal emergence, because you know something on the growth of the area, which I think is not satisfied by any other known family of minimal surfaces. But let's not get into that. Okay. So and then the second theorem is just the very same theorem for the case of the Steklov operator. So that's from this year. I think less than a month ago, actually, with Romain. So same theorem, but now for Steklov. So let sigma be a compact surface. With non-empty boundary. Then there is a smooth metric G on sigma such that we maximize Steklov. So such that sigma 1 of sigma comma h, then the length of the boundary with respect to h is at most the corresponding quantity for G. Well, that's G, right? For any smooth metric. H. Okay, so now let me actually write the theorem on minimal surfaces separately, because I think it's much more striking in this case, because of course theorem A, they were like dating back to Lawson, people knew that could immerse any closed surface minimally even into the 3 sphere, with the exception of RP2, I think, right? But now for this case, so like given any compact surface with non-empty boundary, that was not known before our work, I think. So theorem C is that let sigma be a compact surface with non-empty boundary, then there is a free boundary, there is a, so it could be branched, possibly branched, free boundary, free boundary minimal immersion, from sigma to some Euclidean pole. And so as far as I know, so that could be the first result of this type without any restriction on the topology of sigma. So first such result without any restriction on the topology of sigma. So there have been plenty of results like that using various methods. So let me kind of give you a few of them. So many constructions before. So there has been work by Fraser and Shane, which was in the genus zero case, and so the method was also Steklov. So using maximizers for Steklov. Then there was work by Fola, Bakar, and Solo. And so this uses kind of singular gluing or perturbation or desingularization techniques. So perturbation / gluing. So meaning there's some effective version of implicit function theorem involved. Singularization. And then kind of the same kind of style of techniques. There's Kapulias and Lee. And then, of course, I mean, we're talking about minimal surfaces, so min-max has to be somewhere. So there are also min-max constructions. So by cat over, and more recently, then using actually dense machinery, Colato, Hans, and Kyoto. So and these here are min-max. Okay. But they all have, I mean, so there are two things. I mean, the gain you have is that those actually all get into the 3-ball. We don't know that, we might not. On the other hand, they have restrictions on the topology.
Henrik, I have a question from Dmitry Feifman. In theorem B,
Yeah,
can there be conical singularities?
Yeah, no, yeah, so they can't, and the reason is kind of silly. The reason is that, so even in theorem A, these are not random conical singularities, but they have cone angle multiple of 2 pi, and they're essentially conformal. So they only come from, you have a smooth metric, and then they come in from the differential of harmonic map. So it's like purely conformal. But now for the Steklov problem, that's conformally invariant in the interior. So I can change my metric conformally, and the Steklov eigenvalue is not affected by that at all, because I mean the digital energy is conformally invariant. So I mean, if I have a maximizing metric with such a type of singularity in the interior, I can just change it conformally and don't see it anymore. It's kind of silly. Yeah, I mean, yeah, that's easy to see. So you can also, in theorem A, you can allow like slightly more singular metrics than smooth metrics. So you can also go maximum. I mean, it's the same as the maximizing metric among like the metrics with those singularities. What I should say, maybe not all the conical singularities, but at least the conical singularities of that type, so that you have like cone angle multiple of 2 pi. So yeah. All right, so I hope that answered the question. All right, so then let's continue. So let me give you the strategy to prove these two theorems. And so that basically splits up into 2 parts. So there are 2 things you have to take care of. And the first part has been entirely done by Romain. And then, so the things we do is like, we do the corresponding second parts. So let me kind of start by explaining a bit what Romain has done like over the last few years. So the strategy to prove theorem A and theorem B. Okay, so the starting point is a theorem by, let's consider, because the pictures are slightly easier to draw in that case, I'll emphasize that it's kind of the same. So consider theorem A, so the closed case. So there's work by Romain, and then also some work by Nadia Jafridi and Sia, which is an interesting story in itself, but we only have a finite amount of time, that solve. So what they do is they solve this maximization problem, but instead of looking at all the metrics, they only look at those in a given conformal class. So solving the maximization problem in a given conformal class. And so the idea behind that, I mean, it's kind of this classical idea and these critical problems that it's always better to have solutions to approximate problems than approximate solutions to the problem. So what you actually do is you exploit this connection to minimal surfaces or harmonic maps on an approximate level. So you look at like truncated problems for which you can maximize because you just have compactness of free, and then you get like approximate harmonic maps, and then you can use them to get compactness for your sequence. But it's kind of difficult analysis. But why is it helpful? Because that allows you to do the following. So that allows you to take a maximizing sequence now for the full problem, so maximizing over all metrics of the following type. And now you might also see how the singularities actually come in. So it's of the type GK equals the gradient of a map phi k divided by, so I hope the constant is correct, doesn't matter too much. And so what's this phi k? So where phi k, that's from sigma hk to some sphere of fixed dimension, that's harmonic. And hk, that's the hyperbolic metric conformal to pk. So what is good in that? So you have done the thing you would always do. You have broken up your sequence into the two parts you should use in dimension 2. So the conformal direction and the moduli space direction. And it turns out that one of them you have compactness for free. So there's an argument by Kokarev which tells you that these maps phi k can't have bubbling, and that's the only possible degeneration these harmonic maps could have. So there's work by Kokarev which tells you that phi k, and that's actually where it's important that you work with the first eigenvalues. So that's exactly what starts to be different when you move to higher eigenvalues, that you could have bubbling, and then it gets much more complicated. So phi k cannot develop bubbles, which basically gives you compactness in the conformal direction. So compactness in the conformal direction. So maybe to give you an idea of why there can't be bubbles, if there's a bubble, you prove there's only one bubble carrying all the mass, but then you essentially see around sphere, so then your eigenvalue will limit to 8 pi, but you can prove that you're strictly better than 8 pi. So you have to take care of the other direction. And what's the idea there? So the only possible degenerations, of the metric of the now hyperbolic metric, degenerations of hk are of the type. So, and now that's why I chose to talk about the closed case, because now that's easier to draw. So it could be something like I have a genus 2 surface maybe. And then I have some curve in there, let's say maybe down here, that now starts getting shorter. So maybe this kind of moves into this. And then eventually I degenerate into a surface of low genus. So eventually I degenerate into, how can I draw that? I don't know. Okay, so you have this type of degeneration. But then you can actually use these harmonic maps and some like energy identity in these cuspidal parts where you degenerate to show that. Okay, now I have to introduce some notation. I'm sorry. So right, so the thing I want to emphasize is that here you have seen like that as lower genus now. Right, so I started out with the surface of genus 2 and I degenerate into the surface of genus 1. And that's the only way these degenerations can look like. I degenerate into something of lower genus. Okay, so let's define capital lambda 1 of gamma to be the soup over all the metrics, and then I take the quantity I want to maximize. So I take this on the surface of genus gamma, that's closed of genus gamma. And then basically in this picture here, so if we have star, then one can show, okay, so remember, so that's supposed to be like the conformal structures of a maximizing sequence. So in the limit, you should on the one hand get this quantity. On the other hand, you degenerate into something of genus below. So you should have this. Okay. So now the thing you have to do is you have to prove that's impossible. Okay, so this thing here, so show that this is impossible, that this is impossible. And then the problem for it, so the story for Steklov is kind of very similar. Now you won't have harmonic maps into spheres, but free boundary harmonic maps into balls. But then it's kind of the same picture. The only thing that's different is that the conformal degenerations of surfaces with boundary are much harder to picture. So that's why I chose to draw the closed case. So for Steklov, what you will get for Steklov, so I take, say, we need to show that, so I'll now state the thing we actually have to prove. So the strict inequalities, so we have to show that sigma 1 gamma k is strictly above sigma 1 gamma minus 1 k plus 1, and sigma 1 gamma k strictly above sigma 1. So my notation is slightly inconsistent, I'm sorry about that. But I don't want to write capital sigma for the eigenvalue because capital sigma is the surface of me. So okay, minus 1. So that is now, this is the max for the soup. Write soup, right? That's the soup on the surface of genus gamma with k boundary components, So again, these inequalities correspond to the way that the conformal type can degenerate. Oh yeah, so right. So the question is if you could have degenerations which disconnect, you could have, but then you can prove that all the mass goes into one component. And then you just look at that component. But that could happen. Okay. So I should emphasize that all I've explained up to this point, that's complete. I have nothing to do with that. That's all Romain's work. So that's all work by Romain Petrides. Okay. And I mean, he has also done that for higher eigenvalues, where you have to take care of the bubble, so which is much more technical and much more complicated. Okay, but now let's actually state the theorems giving you these inequalities, so because that's the technical things that we proved recently. So there's theorem A prime corresponding to theorem A, which is the thing that we actually prove. So and we phrase it more general. So we just say, well, the thing you have to do is you have to show that this quantity lambda 1 times area strictly increases if you change topology. And then of course you can apply induction and get like maximizers and then like prove these strict inequalities. So given any closed surface sigma, so with a metric G. So G here, I don't want to write down again, is allowed to have the singularities that you need for the theorem. So like these finitely many conical singularities. So let sigma prime be obtained from sigma by attaching a handle or a cross cap, or I should say Möbius band, handle or Möbius band. So then there is a metric G prime on sigma such that lambda 1, so it's a smooth metric, so that you strictly increase this quantity. Okay, and so if you have that, then you just get theorem A using induction and Romain's work. So then theorem A follows from Romain's work combined with induction. Okay, and then theorem B prime, very same thing for Steklov. So theorem B prime is so here, so the more robust way to formulate is that you just have to attach a rectangle along two opposite sides of the boundary. So I'll draw pictures in a second. So given any compact surface sigma with non-empty boundary, okay, so should have metric. Let sigma prime be obtained from sigma by attaching a rectangle along two opposite sides of the boundary, two opposite sides of the boundary. Okay, then again, we can strictly increase that quantity. So then there is G prime on sigma prime such that you strictly increase. So such that lambda 1, sigma 1 of sigma G, the length of the boundary, is strictly below the quantity for sigma prime, for G prime.
When you say two opposite sides of the boundary, you mean they have to be on the same boundary component?
Let me draw a picture, okay, and then talk about exactly that question. So let me draw two pictures. So the picture. So let me first of all draw the picture for theorem A. So I'll discuss your question in a second as well. So theorem A, the picture is that you have a surface, and then you just pick like 2 points, like here and here, and then you just attach like. Okay, so that's the picture for theorem A, and so for theorem B, so that's the orientable case. So for theorem B, so it looks a bit weird at the first moment because if you go back up here, so for Steklov you have like this multiple conditions, but now the theorem only says, well, blue rectangle. But the point is exactly that I can do it in whatever way I like and it'll be fine. So the analysis is the same. So for theorem B, you would have something like a surface with boundary. And then maybe I also have some genus somewhere. And then I can do exactly this thing. I can pick my points wherever I want. So I could pick my points like here. Let's call them maybe P and Q. And then I would attach a rectangle like this. Okay. But then I can do all sorts of things to this. So I can choose P and Q to lie in different boundary components or in the same boundary component. And I can also reverse the orientation of one side that I attach. So we can choose P and Q in the same or in different boundary components. And can also reverse orientation. And then by like doing all of these things, you get actually all the inequalities you need. But the analysis is the exact same. It doesn't depend on if you attach like different boundary components or if you reverse the orientation of one of those charts. It doesn't matter at all. All right. So let me mention here that for theorem B, there's some somewhat related, but also somewhat in different direction work by some people. So there's some recent work related to theorem B prime by actually two groups. So there is Giroir, Lagacé, and then there is Kapoukin and Stern. So I actually think Daniel is going to give a talk here in like maybe early July. And so so I don't want to get into what they actually prove. So they get some information on the sharp constant in these bounds. So on these numbers, in other words, on the corresponding numbers. So on these numbers, so sigma 1 gamma case, they get some information on those numbers and kind of can prove in some cases what the limit is as like some of those quantities go to infinity. Okay, so they get some information on asymptotic behavior of these values, sigma 1 gamma k. And so I think what's interesting is that, so both of them are very different methods. So Giroir, Lagacé is homogenization, and Kapoukin Stern is kind of min-max style for controlling the volume. It's kind of interesting that there are all these different techniques around this problem. Okay, so then let me try to kind of in the last 20 minutes give you an idea of how you could try to prove these theorems. And so if you go back here for a second, so these theorems look basically the same. So that might ask, so why it's like 2 different years, 2 different papers. So I think now you can take the proof of theorem B prime and copy it almost symbol by symbol for theorem A prime. Not quite, but I mean like very limited amount of work. So it doesn't work the other way around. So you can't go from theorem A prime to theorem B prime. I mean, using the techniques developed at that point. So they were just not sufficient to get theorem B prime. And maybe I'll try to emphasize later a bit why that's the case. But now there should be like a unified picture for all of this. Okay, so the first step in proving these things is figuring out how not to prove it and understanding why. So, so step 1 is how not to prove theorem A prime. So again, so this is jointly with Anna Siffert. And so maybe, yeah. So not to prove that theorem A prime. So yeah, so let me tell you how not to prove it. So here's how not to prove it. So I could try the following thing. I could start with the surface sigma. And then I could start changing the topology as follows. So I take like points, let's call them x0 and x1, and then I attach like this thing. So I attach this thing, so I attach this like here. So that is C epsilon 8, which is a sphere of radius epsilon times epsilon times an interval 0, 8. So just with the flat product metric. And so you attach along, along the boundaries of these balls. Okay, and let's call the surface that we get, let's call the surface sigma epsilon 8. So now the thing you can do is, so of course, if you look at the surface, so for the area, you gain roughly epsilon, right? So the area of this, that's comparable to the area of sigma, and then you'll have a term on scale epsilon. So you'll have something like 2 pi h times epsilon, and then like plus O of epsilon squared. So what you can now do is you can also study the asymptotics of the first eigenvalue. So the question is asymptotics for the first eigenvalue. So and then actually the more important thing we'll learn from this is why. Okay, so so we have to prove what happens and we have to really understand why. So and there are 2 very different cases. So there's case 1, which is kind of might not happen to you for the maximizing metrics. So you have that phi at these points. So you have some symmetry on all the first eigenfunctions. x1 equals 0. And you have this for any first eigenfunction sigma. So for any first eigenfunction on sigma. So then you can actually use that construction to prove theorem A. So then we can use this family to obtain theorem A prime. But it might just not be true. So we might have the case that we are not able to find 2 points having this property. So case 2 is that that's not the case. So case 2 is that there is phi naught a lambda 1 sigma eigenfunction. So non-trivial, of course. Eigenfunctions such that you have that phi naught at x naught plus phi naught of x1 is not equals to 0. Okay, so now let me kind of make things a bit simpler. So let's assume for simplicity that the multiplicity of the first eigenvalue is equals to 1. So of course, I mean, it's kind of silly because then I could always choose the points x0 and x1 such that I have this condition. So have that being 0. But on the other hand, the arguments are basically the same. If you have multiplicity 1 and you choose points in this bad way, then the general case is just easier to keep track of things because there are not like too many other eigenvalues around. Okay, so here's the theorem in that case. And I'll give you the theorem by drawing a picture. So the work was actually done a bit longer ago. So the work was done in 18. It says that in case 2, we have that. So and now I'll just draw you a picture giving you the asymptotics of the eigenvalue of this family. So in this picture is as follows. So let's put here, that's 8. And here, let's put square root of lambda. So then you'll have the following things. So you'll have somewhere here, like lines, that is lambda naught of that. So that's the first directly eigenvalue of the thing that I attached. And then I also have somewhere here, just the first eigenvalue of the surface. Okay, so that's the picture in the limit. But how does the picture actually look like before I take the limit? And the picture looks as follows. So the first eigenvalue starts out here and then moves down here. And the second eigenvalue starts up here and then moves like here. So this is lambda 2, sigma epsilon 8, and this is lambda 1 of sigma epsilon 8. And then, so the thing that is important, of course, is that the scale here, so the size of this, this thing that I lose, so that is comparable to epsilon to the 1/2. So remember, epsilon is the gain in area. So I lose more in the eigenvalue, so I lose. Okay, so which implies that, so this implies that lambda 1 of this surface, if I multiply by the area, that actually goes strictly below the 1 of sigma in that regime. So there's no way you can prove the theorem in that regime. So let me put here. So the point where they intersect. So let's call this point here H lower star. So there's no hope, at least for these parameters near H star, to prove that theorem. So let me make a few remarks on that. So, so the first remark is that we expect that we can obtain this theorem, so that we can obtain theorem A prime only with parameters, H near H star. And so the reason for that is that, and you really see that if you go to the estimates, is that in a way, that's the parameter where you see the change in topology on a spectral level. And of course, that theorem has to use that you change the topology, otherwise, I mean, it's impossibly true. And so these parameters are those where I can observe that on the level of the eigenvalues. So that's where we can, observe the change in topology on a spectral level. And then the second thing, which is kind of the more important thing, is that where does this scale come from? So so the scale epsilon to the 1/2, so it originates from the following term. So if I take this quantity, that's comparable to epsilon to 1/2. So what's psi epsilon H? So where psi epsilon H is a normalized lambda 0 C epsilon H eigenfunction. All right. So okay, so that means just that, look at this term. So if you want to follow this idea, so that you want to like attach something degenerating and study the asymptotics, and look at those parameters where you see the change in topology on the spectral level, the thing you have to attach has to be better in this scale. So it has to be below epsilon, which is the term of the area or the length of the boundary in that term. And so so that's the good news. You know what you have to find. Here's the depressing news. The depressing news is that, so where that comes from is just that the way the collapse happens on this flat cylinder is that you just collapse in one direction. Meaning that at some point the eigenfunction just comes from, you have the eigenfunction on the interval and you rescale that. And to make it normalized, you have to rescale exactly by that power. So that's where it comes from. But now that's kind of a phenomenon that you have as long as you limit to something with like an isolated eigenvalue at the bottom of the spectrum. Meaning that the only way you can beat this term is that you have to glue something which starts seeing non-discrete spectrum. So that implies, so in order to have a better scale in this star-star, so we need to attach a degenerating part developing a non-discrete spectrum. Otherwise, you just will have that term on scale epsilon to 1/2 and just lose. Okay, so now what is our actual construction? So the actual construction is that in the closed case, we just use a truncated hyperbolic cusp. So closed case, so we attach a truncated negatively curved cusp. So here is the curve. So the curvature that comes with a parameter kappa, which corresponds in comparison to the previous construction to the parameter h. So that's the additional parameter that you have. Okay, and so let me recall here for you that if I take the standard hyperbolic cusp, so I take like x, y in the hyperbolic plane, where y is at least 1, and then I mod out the translation x maps to x plus 1. So that is just something like this, and then I take this infinite cusp. So that has continuous spectrum, one quarter up to infinity. So now what you do is you truncate this in exactly such a way that you can observe the formation of a continuous spectrum on like a specified scale, and then you can like get into the estimates. So for the Steklov case, so what we attach is so we attach a cuspal domain of the following type. So I take the plane and then I take a region like this. So again, I'll truncate that. And so that is, so the region that's all the points in the plane where y is non-negative and minus y squared divided by 2 is at most x, at most y squared divided by 2. So, and that was introduced by so Nazarov and Tuskinen, and they actually proved that you have non-discrete spectrum here, so non-discrete spectrum. So, but in the actual estimates, we use way more than the fact that you have continuous spectrum. So you actually have to go back into that construction and like do finer estimates. Okay, so let me try to give you a very brief summary of the steps how we actually prove theorem B. So how do we prove? How we prove theorem B prime? How we prove theorem B prime? Okay, so there's step 1. So that is just good upper bounds on eigenvalues. So that's just a classical test function estimate. But it's important that you have really good upper bounds for reasons I'll not be able to explain. So then step 2, but it's not super hard to obtain these because you basically know what you expect your function to look like in the limit, And then you can use that function, like interpolate in a good way as test functions. So then step 2 is pointwise estimates. Pointwise estimates on eigenfunctions in the attachment region. So the estimates at this stage that you obtain are also not terribly hard. It's basically like sigma, so the surface you use is compact, and then you have like elliptic estimates, and like you know how you can use like scaling to like bring the attachment region on a fixed scale, and then you just get an actual kind of scale invariant estimate. So also not terribly hard. So then the hard work starts in step 3. So step 3 is that, so using the first 2 steps. Okay, and so let me emphasize the way you use them. So step 1, so that's just an energy bound, right? And step 2, that's some type of control on the boundary values. So that's control on boundary values to obtain an asymptotic expansion of eigenfunction, eigenvalue, and eigenfunction in the Caspel domain. All right, so I didn't mention that. I should have mentioned that of course these things that we attach, you make them degenerate, right? So the hyperbolic cusp, you like take a circle of radius epsilon, and also you rescale this Caspel domain in an appropriate way. So so the crucial point here is that, so you have the energy bound, which is good energy bound, you have some control on the boundary values, and then plus, I mean, so or maybe say in a good choice of coordinates, so in a good choice of coordinates. So then step 4 is, now that you understand your eigenfunction to some degree in this region where you attach, so let me kind of draw a picture. So step 4 is that I have this point in the boundary, so like that's like here I have sigma, and then I have my point where I attach P, and then I have this Caspel domain here. So like going off here. So and this here will actually be of scale epsilon squared. So now the thing I've gained is that now I also have some information on my eigenfunctions, say in this region here, so in this region, right? So here I know, so step 3 tells me I know better what's going on here, and now I can use that to improve my pointwise estimates from step 2. So step 4, so you can use this picture to improve the pointwise estimates, to improve the pointwise estimates. From step 4. And then there's the last step, so step 5 is that, well, you write down a test function. So you build a test function out of the first few eigenfunctions. And let me say one thing about this. So the point is that, of course, if you want to estimate the first eigenvalue, you need to satisfy one linear constraint, namely you need to be orthogonal to the constants. Now, the most obvious way to try to achieve that is, well, you just subtract the constant. The problem about that is that now you perturb your equation on a scale, which is basically the length of the boundary to the power 1/2. The gain you have is by doing this in step 5 with another eigenfunction is that the scale in which you perturb your equation is much, much smaller. And that is because you have this phenomenon of continuous spectrum forming. All right, so that's all I want to say. Thanks for your attention.
Thank you very much, Henrik, for this talk. Does anybody have any question for the speaker? I have a few actually. So I was wondering, those cuspidal constructions, how sharp are they, in the sense that is it only this specific power of the cusp that will work, or would you have a range of parameters that you can play with in this type of construction?
Yeah, you can. So I mean, we didn't have that. I mean, so we do it for a range of parameters. Probably you can do much better, but we didn't care too much. But yeah, you're totally right. So so there are different things you can play around with. So I think the thing we actually do is that the level we truncate. So there we have quite a wide range of parameters where this thing works. But yeah, I mean, there should be like, I actually think that picture should be much more general. So in a way, so what we're doing here all the time is that, so if I go back here, we are basically tracing that picture. So the thing that you have in mind is that that picture should become the same picture, but it's much harder to prove that once you move like to a smaller scale. But basically, I wouldn't be surprised if the picture is always like that, with the blue gap being exactly the scale. I mean, where you take the non-derivative. I wouldn't be terribly surprised by that, but it's hard to prove.
Yeah. And I was wondering also, so obviously questions of maximization in higher dimension, we don't really have any theory about that or any of that, but in theory, the perturbation theory could still go through. Have you thought about topological perturbations in dimension 3 and higher of this type and the kind of things that you would need for that?
Oh, we have not. So I mean, it's kind of robust. So we might use every once in a while conformal invariance of Laplace dimension 2, the conformal covariance, but I'm not convinced that it's terribly important. So I mean, on the other hand, the question is kind of ill-posed, right? I mean, yeah, well, it depends. I mean, so because if you just, I can even make bigger among all the metrics on a given manifold, right? And then I can just attach something and converge back. So it's not really clear what the right question to answer is. But in a way, so that's, but on the other hand, so the positive answer is that you could cook up Boolean constructions and do very similar asymptotic analysis, I think.
Right. Are there any other questions for Henrik, either over voice or in chat?
Oh yeah, Sumisha's asking something about all the higher eigenvalues. Yeah, so there are different answers to that, right? So the first answer is that, I mean, certainly there will be like types of things that you can't obtain because we know that there are examples where you don't have a smooth maximizing metric. On the other hand, there should be some cases where you can do it. But it's harder, but yeah.
So,
can I ask you a question?
Yeah. Who is speaking?
It's Vlad. I'm sorry.
All right. Yeah, you can ask a question. Ask away.
Yeah, I'm sorry. When you attach this strip to different boundary components, so it corresponds to attaching one handle and killing one boundary component, right? So, and the question is, either it just corresponds to killing one boundary component, depending on how you attach this strip. Can you say what happens if I attach just a handle? What happens to the Steklov spectrum?
You mean in the interior, or?
Yeah, if I attach a handle interior to the interior.
Yeah, I mean, so in a way, the Steklov spectrum is not very sensitive what happens in the interior.
Right, but so you want to say that it doesn't change at all?
I don't know.
So it's not known.
So let me say, I would be very surprised if you could prove that type of monotonicity thing using that construction for attaching handle. Because I really think you need to see like the change on the boundary. But yeah, so yeah, that's what I think. Is it okay?
Okay. Yeah, I agree. Thank you very much.
All right. Are there any other questions? Yeah, I'll piggyback on Misha's question. So you're saying in some cases you would expect for higher eigenvalues that you would get maximizing metrics. So what kind of situations would that be?
No, I'm sorry. So that's not what I'm saying. So what I'm saying is that so for higher eigenvalues, these kind of inequalities indeed are kind of complicated, right? and we know that some of them can't be strict.
Yeah.
So for instance, there's the recent work by Fraser and Shane showing that so you have no smooth maximizing metric, say for Steklov, for high eigenvalues on the disk.
Mm-hmm.
So the corresponding inequalities can't possibly be strict. But then so on the other hand, there might be still some sort of Boolean constructions where you get these strict inequalities also for higher eigenvalues.
Oh, right, yeah.
But it will be more complicated because, I mean, of course, you need to kind of see I mean, you will have to see some type of obstruction, right?
Yeah.
So you have to kind of get your hands on that and understand how that enters into the analysis.
Mm-hmm. Yeah, for
sure. Sorry, that's Misha. Yeah, so that's exactly what my question was about. So if you try to just do monotonicity in genus, right? So do you expect any significant differences between the first eigenvalue and higher eigenvalues?
Technically, yes. So technically, you need to work harder to a level where you start seeing those obstructions. So the machinery we have at this point will not be able to identify those.
You expect to have other abstractions other than just
yeah, I mean, so yeah, I mean, so meaning that, so for the first eigenvalue there's no obstruction, right? But then for higher eigenvalues, at some point you need to see something, right? So for instance, if I do the kind of yeah, so So maybe let me, okay, so let me say one thing of this type, which maybe helps, is that, we are working with the first eigenvalue, right? And we have this one parameter kappa, and then we can play around with this parameter. And then we have also one linear constraint, so you have to be orthogonal to the constants. But now if you move to higher eigenvalues, the story gets more complicated, right? There are more obstructions. I mean, more linear constraints have to satisfy.
Right. But I think you still expect monotonicity in genus to hold, right, for higher eigenvalues.
Maybe, yeah. But I mean, you have to put in some more technical work.
Right. Okay.
Yeah.
Mm-hmm. All right. Are there any other questions? Well, that seems to be all, and quite a lot of them. Thanks, Henrik, for the talk, and thanks everybody for being here this week. Next week we will hear from Shaisa Kansani, and we will send the abstracts in the next few days. Thanks, everybody.
Thanks.
Thanks.